our last week lecture. I think it's not going to, we have another maybe 40 or 30 something slides to finish today. We're going to continue about the non-enzymatic browning reaction, which is one of the reaction in this non-enzymatic browning is Maillard reaction. Just to recap from our first previous last week lecture, that we already talked about enzymatic browning, which requires enzyme in order for the reaction to start. And after a while, when it reach the production of quinone, if you remember, that step forwards until the formation of the melanin compounds are no longer require the enzyme. So that is the enzymatic browning. For this part, non-enzymatic browning, there is no enzyme present or required for this reaction to undergo. This Maillard reaction. So the Maillard reaction is an organic chemical reaction. The figure shows you, kind of like a simplified version of the reaction. The reaction is very complicated. It involves lots of intermediate compound. Hundreds, if not thousands, of compounds can be generated from this Maillard reaction. You don't need to know all. What you need to know is just the principle, the basic, the main steps for this reaction. It's too much for you to understand or to memorize all the compound. Even me, I don't, maybe if not even 20% of the compound that I can tell the name. That's too much. Okay, the Maillard reaction is an organic chemical reaction in which reducing sugar, if you remember from last lecture, we need reducing sugar to react with amino acid in order to form a complex compound or mixture of compound, and the final compound is melanoidin. So this reaction is responsible for that give the characteristic flavor, and it also give a characteristic aroma of the brown food or the browning of food that you can smell, you can taste from your food. So the Maillard reaction is named from the base get its name from the chemist, French chemist Louis Camille Maillard, and then he's the one of the first scientists that come up with the general idea on what happened when you prepare the food product, what happened in terms of the sugar and amino acid reaction that generates this type of product aroma that give you a lot of distinctive flavor and smell of the food product. So, so in general, this reaction can be called and can be classified as a non-enzymatic browning reaction that required an optimum temperature for this reaction to have an optimum condition for this reaction is from around 120 degree to 165 degree. This is based on the studies that being done previously. So within this range of the temperature, the browning reaction can have its optimum rate. So I also mentioned last week that it is important to note that Maillard reaction, this Maillard reaction is difference between the caramelization reaction, because it proceeds at high temperature, as well as it involves pyrolysis of sugar for the caramelization. Caramelization, doesn't require the presence of amino acid. So you can have lots of several flavor compound formed during the Maillard reaction. So this compound later can be break down to yield another flavor. So for example, this reaction can, you can go forward, in this direction. You can have lots of compound, and then this compound in turn can produce lots of other compound, thousands of different compound. Okay, it depends on the type of food, types of sugar in the food product, type of amino acids. All of these can determine the rate react of the Maillard reaction. Also can determine what type of product that can be produced from this reaction. All right, so the Maillard reaction occurs in three main steps. The first initial step, we call it as the formation of N-glycoside. N-glycoside is when the sugar react with the amino acid, for example, the glucose. When you have glucose in your food, for example, in your meat, and then you have amino acid. Amino group comes from the amino acids, react with this glucose. You can have the initial step, you will produce glucosamine. In general, we call it as glycosamine, meaning that glyco is a sugar combined with amino group from the amino acid. So the first initial step, the first step is initial step, formation of N-glycoside. The carbonyl group of the sugar reacts with amino group of the amino acid, producing N-substituted glycosylamine and water. These two are the product of this first or initial step of the Maillard reaction. So now the glycosamine is produced, and it can start the second step of the Maillard reaction. After the formation of N-glycoside or glycosamine, as we called it, the ammonium ion is formed, and then this ammonium ion then isomerize. So during this stage, this isomerization of the reaction of this second stage is called as an amidary arrangement. And during this second stage, the product that can be formed is called ketosamine. So this ketosamine undergo further reaction via several pathways. So this ketosamine can after that undergo further reaction via several pathways, and one of the pathways can produce a reductone, butadiene, methyl glyoxal, and other lots of other short chain hydrolytic fusion products such as diacetyl, acetol, pyruvaldehyde, which these can undergo another type of reaction that's very important in this Maillard reaction step, which is called Strecker degradation. Strecker degradation. So Strecker degradation. So from this Strecker degradation, it has several other chemical steps that will eventually produce hydrolytic fusion and melanoidin products. So the ketosamine can also go on to form melanoidin and other brown nitrogenous polymer. So these will impart the characteristic brown color to the food. What you can see from the food, for example, toast. Your toast is called by this very reaction that I just mentioned. So lots of other products, not one. You can have toast, different taste, different smell of the toast, right? If you do barbecue, you can have different type of characteristic of the smell and the taste. If you fry your what we call it French fries, you can have a different type of smell as well. Right. All right. Then in the process, hundreds of different flavor compounds are created. So these compounds in turn break down to form yet more new flavor compound and so on. Up to now, still scientists still not capable to identify all the every single compound that can be produced from this Maillard reaction, because it can produce lots of different compound. Every year scientists will 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 uh, will come out, will identify a new flavor compound from this Maillard reaction. So each type of food has a very distinctive set of flavor compounds that are formed during the Maillard reaction. So it is these same compounds have been used over the years to create artificial flavors. So this is how they, from this, for example, barbecue, right? Right. So if you do if you make a barbecue at your home, you know that how barbecue tastes like, right? You know how when you eat your grill meat, or your grill barbecue meat or chicken, you know how it tastes. You know that this is barbecue product. If you fry your chicken, you know that this is, without looking at, if you look at the chicken, you know that this is a fried chicken, this is a barbecue grilled chicken. But without looking, if you just taste it, you can straight away determine whether it's a fried chicken or barbecue chicken. So based on this, flavor that created during this Maya reaction, when scientists did identify using GCMS, HUPLCMS, they know that what type of compound that give this characteristic flavor of this barbecue taste. So that is how, and then they produce the artificial flavor that mimic this compound that comes from the Maya reaction. So that's why if you buy a potato chip, for example, like what we call it now, cottage fries or Pringles, or if you have lots of extra money, you can buy Lay's or Ruffle, lots of different in outside European American potato chip product that can have, sometimes you get barbecue flavored potato chip. They are definitely, they not barbecue the potato chip. They just mix the potato chips with the artificial flavor that they created based on the Maillard reaction compound. All right. Same goes to, like, if you have um, um, what we call it, chicken flavor or prawn flavor. Sometimes they have lots of other different type of flavor that you can buy for your potato chip. All of them, use the artificial flavor that mimic the product of the Maya reaction. All right. Um, so in an amino group of an amino acid, NH2 reacts with an aldose. It can react with keto sugar as well to form and substitute glycosamine, which is a colorless product plus sugar, plus water. This and then altered in what is known as an amino rearrangement to form and substitute one amino 1 deoxy 2 ketose compound. This is the long name of the amino product. So this is an isomerization reaction and is essential for browning. So first, what you need to memorize, or you need to understand, is just, first you have an amino acid react with sugar, produce N-glycosylamine, and then this N-glycosylamine will later on, the second step, will undergo amino rearrangement to produce this N substitute 1 amino 2 deoxy 1 deoxy 2 ketose compound. So what type of reaction? The amino rearrangement is an isomerization reaction. So this is what you need to know. All right, what we have here, I think it's the same thing. I just repeat it again. So an amino group of amino acid react with aldose or ketose. This is how, if you can see, let me make it slightly bigger. So if you if the reaction start with glucose, that's reducing sugar, plus amino acid, you can have glucose glycosylamine or glucosylamine. If you start with fructose, react with amino acids, you can have fructose glycosylamine or fructosylamine. So when you have glucose produce glycosylamine, these first two that if you can see my cursor, this is the first step of the Maillard reaction, and then this glucosylamine will then move to second step of the Maillard reaction, producing one amino 1-deoxy D-ketose. Right, I hope you understand up to now. So step in Maillard reaction, and then analyzation reaction, formation of hydroxymethylfurfural HMFs, which take place in a series of degradation and condensation reaction that result in melanoidin. So after the Amadori rearrangement, you can have the next step is analyzation. This analyzation, can produce lots of, can have this analyzation is just general reaction. In this analyzation, there's a series of degradation, condensation, that at the end of the day it will produce melanoidin. So and then the formation of oxulose. Oxulose is a compound that contains two carbonyl group. This oxulose produced from this amidary rearrangement will not going to have the same fate as the rest of the product. This oxulose uh, uh, will have a different part of reaction, which is will enter the structural degradation reaction. So we're going to talk about the structural degradation next. Just a second. Just a second. Yeah. All right. Sorry. Okay, this is the overview. This is quite complicated. Just to show you, all the direction you can have from the amidary arrangement. You can have shift-based reaction. If you go back to your chemistry lesson that you have before, what is shift base? Shift base is a compound. During this Maillard reaction, at the stage of amidary arrangement, you will this reaction of a rearrangement of amidary rearrangement will produce shift base compound. Shift base compound is if you go back, or if you can't remember, just Google what is shift base. It's considered a subclass of imine. Sometimes they call it the shift base, or they can be called imine, being a secondary ketoimine or secondary aldehydes, whether it's ketose or whether it's aldose. Sometimes it's synonymous with the azomethane. So you can generate lots of different compounds after the amidary rearrangement. So after that, you can have keto form, you can have eno form, and then analyzation, deamination, dehydration, analyzations, lots of complicated chemical reaction. And then when it's produced oxulose will enter the structural degradation. What is structural degradation? So this structural degradation is involve amino acid again, but this time around, instead of just one carbonyl group of amino acid, this structural degradation involves the sugar to react with the molecule with two carbonyl group. So before this, at the start of the reaction, we are only talking about one carbonyl group react with sugar, right? So this time around, when it comes in to the structural degradation pathway, this pathway requires two carbonyl group to react with the sugar. For example, two carbonyl group compound such as oxulose. So the compounds begin to trade part of themselves. I will show you the mechanism, the you know the structure after this. So one of the carbonyl group ending up on the amino acid, creating an aldehyde as well as an amino ketone. So this is an intermediary stage, and reaction continue to create many different volatiles. So who's come out with this name? These guys here in 1822. Sorry. So these guys, Adolf Streicher, I think is German. Adolf, I think. The Streicher degradation is a reaction between alpha amino acid, alpha amino. I hope you know now. At this stage, you know now what is alpha amino acid, and dicarbonyl. Dicarbonyl is two carbonyl compound, usually produced through the Maillard reaction, and has been well studied in food chemistry. And it produces volatile flavor. Lots of volatile flavor, hundreds of thousands volatile flavor can be formed from this degradation uh, in many products that undergo Maillard browning or Maillard reaction. For example, here you have diacetyl butadiene. You know that this, I hope you can see it clearly. Let me make it bigger. This compound, if you see at the structure, it contains two carbonyl group, right? So when it has two carbonyl group, that is going to enter structural degradation. For example, if your amino acid contain valine, it will react with valine. You know, um, when it react with the valine, the reaction will produce this compound. So it binds at the alpha amino group here. All right, so alpha amino group, and then it can have subsequent reaction, and then if you start with the diacetyl or butadiene, when it react with valine, the end product that you will have is tetramethylpyrazine. I can remember this tetramethylpyrazine smell. It's a very famous compound. Um, Sorry, I can tell it now. So this is a very famous compound, a very well-known compound that have very distinctive, that give distinctive, characteristic of something that very well-known. I can remember. Sorry. So this is how it looks like on the structure degradation. So it can start with different type of compound here. It can start with different type of amino acid here, and then hence you can generate lots of different volatile compound. The reaction between an oscillose dicarbonyl compound with an amino acid gives rise to aldehyde. Aroma of bread can give the distinctive aroma of the peanuts, cocoa. You can produce carbon dioxide, nitrogen containing cyclic compound which condense and polymerize to form melanoidin. So before it can produce melanoidin, during the structural degradation, same goes with again I will repeat that the amino arrangement will produce shift based compound in the form of imine or ketoimine, aldosimine, or you can produce two carbonyl group compound that later on will enter structural degradation. So this shift based compound eventually will produce melanoidin, and in between they will produce some other compound as well. So same goes with secondary degradation. Secondary degradation will produce more compound compared to if you start with shift base, or if you start with reductone and etc. So during secondary degradation, the end product will be the same in the form of melanoidin, but in between the product that can be formed from secondary degradation is a lot more than if then the pathway not in secondary degradation. So again, this is how it looks like: dicarbonyl, amine, saccharoaldehyde, rich nutty meaty flavor. So I think this is easier. This is make it easier for you to understand, a guide to the Maillard reaction. Maillard reaction occurs during cooking, responsible for the non-enzymatic browning of food when cooked. Actually consists of a number of reactions, can occur at room temperature. It can occur at room temperature, but it's very slow. Optimum temperature between 140 to 165. Three stages. First, carbonyl group sugar react with protein amino acids, producing N substitute glycosamine. You can see the reaction here. Next, the second step, the glycosamine compound generated in the first step isomerized. This compound will be isomerized by undergoing a Maduri rearrangement to give ketosamine. So this glycosamine will be isomerized, and then we produce 1,2-enamyl, which is intermediate product, and then we'll have to give ketosamine, and then next ketosamine can react in a number of ways to produce a range of different products, which themselves can react further. Fission product, reductone, hydroxymethylfurfural. So, for example, here the Maillard reaction produce hundreds of products. A small subset of these contribute to flavor and aroma, some groups of which are described below. Melanoidin are also formed, brown polymeric substances which contribute to the coloration of many cooked products. For example, here pyrazine, this is responsible for the cooked roast toast. If you roast your beef or your chicken, roasted chicken, if you toast your bread, what you smell is comes from pyrazine. So pyrroles give you cereal like or nutty flavor. Alkyl pyridine, what give you bitter, burn, astringent. Acyl pyridine, cracker like, when you make a cookies at home, you can have these compound that give the distinctive flavor and smell. Puranone, caramel, burn, furan, meaty, burn, caramel-like, oxazole, thiophene. These four, this is just a small example of the compound that can be produced from this Maillard reaction. So this is, the most famous one, I guess, that that you can smell every single day at home when you cook something. So we know that Maillard reaction is desirable in order to give you the taste or the smell that characteristic of the food that you cook. But this Maillard reaction also can produce mutagen in the form of acrylamide. All right. For example, here asparagine. If Maillard reaction undergoes with starts with asparagine, we can have aldehyde, and later on at the end product is acrylamide. So acrylamide is a highly carcinogenic toxic compound. You know, uh, even I can remember the LC50 of this acrylamide, but acrylamide can cause is a carcinogenic compound. That is why nowadays, if you try to find lots of research trying to identify the amount of acrylamide in the pre-processed food. So sometimes they make they study, they identify that they take for example French fries. They try to identify how much acrylamide can be formed if you fry these French fries, in order to remove all the food product that can produce a high amount of acrylamide. We know now by now you know what is Maillard reaction. Now, what drives the Maillard reaction? You know that sugar and amino acid drive the Maillard reaction. It depends on the type of sugar as well. So if you start with 5 carbon sugar, 5 carbon sugar can have a higher rate of Maillard reaction compared to the 6 carbon sugar. pentose higher than hexose, hexose higher than reducing disaccharide, and mannose. For amino acids, lysine can drive myeration faster than cysteine, faster than isoleucine, and isoleucine and glycine about the same rate. Right? It depends on these two types here. If you start with pentose, you start with lysine, you can have myeration very quickly. The rate will be very high, very fast. Next, water activity. Apart from these two that obvious, reactant for the Maillard reaction, which are sugar and amino acids, this reaction also can be driven by the water activity. So how what does this all have to do with the water activity? So how water activity can influence the rate of Maillard reaction? So we know that from the previous slides that I show you, during the first stage of the first step of the reaction, you produce glycol, amine, and the byproduct is water, right? So water is a byproduct of the reaction. So this and X slow down the overall reaction. So when you produce lots of water, when the water activity is too high, this in turn will slow down the overall Maillard reaction. In general, the higher the AW is water activity, the slower the overall reaction. At lower water activity, the mobility of the reactant is reduced. This is because when you have too much water, it's kind of like dilute the sugar and the amino acids, which are the reactants for this product. So if you have low water activity, you can have if you have too high water activity, you slow down the rate of the reaction. So at lower water activity, the mobility of the reactant is reduced, or the concentration are increased as water removed. So therefore, Maillard reactions commonly occur in dry or intermediate moisture of food between water activity of 0.5 to 7. Above 0.7, or if it's the water activity is 0.8, it will reduce the rate of the reaction. So as the water activity approach 0.7 in all substances, for example, or if you take a meat or a coffee, for example, the rate of myeration and sugar browning peaks. 0.7 is the peak of the water activity that give the peak of the myeration. So higher than 0.7, myeration slows down because the reactant are diluted by too much free water. So for example, I read about coffee recently about the 0.7 water activity are required. It's considered, fully safe for the microbial activity. It's too much water, you can slow down the myeration. Too much water, you can have, you can generate an environment for the growth of the microbe, which we don't want. Okay, and then this, if you have too much water activity, you can have microbe growing, and then it's not desirable for the product for shipping and storage. So that is why the food producer try to, to maximize the rate of my reaction during the storage, by decreasing the water activity. Next, what else? Acidity, the pH. Many of the byproduct of the reaction can alter the pH of the system. So the pH, you need to have a buffering capacity. Alkaline pH favors browning, while acidic pH prevent browning. This is because the freezing and dehydration and buffer precipitation, while acidic pH, will prevent browning or slow down the browning reaction. So therefore, evaluating pH on overall reaction is challenging, and strong buffers are needed. Generally, the lower the pH, the slower the reaction. If you try to have Maillard reaction, you will have to prevent the acidity pH. However, acidifying food system will not completely stop the reaction, and characteristic colors and aromas may be preferably formed under slightly acidic condition. For example, lemon juice can brown during storage by Maillard reaction. If you remember, I mentioned last week that this reaction cannot be stopped. You know, like the enzymatic browning, you can stop it by denature the enzyme, right? If you denature the enzyme, you can stop the enzymatic browning. But this Maillard reaction, non-enzymatic browning, you cannot stop it because the product is there. You can just slow down. Even if you put, acidic pH, for example, lemon juice. After a while, even the lemon juice can brown during the storage because it cannot be stopped. Only can be slowed down. So effect of pH on the reaction, heated with the glucose, lysine and arginine heated with the glucose, the temperature 1 to 1 degree for 10 minutes, increase the pH with the basic amino acid will drive the reaction and increase browning. So lysine, if recall the last earlier slides, lysine is the most preferable amino acids for the browning reaction. And then temperature. So temperature is very vital for browning reaction. High temperature favors browning. Low temperature slow down browning. So if you, I've mentioned about 140 to 165 degree will give you optimum rate of Maillard reaction. The activation energy, most chemical reaction are overcome under most food processing condition. Temperature is a major driving factor for the reaction, but the reaction requires other contributors as well. Heat in combination with high pH, low water activity are perfect criteria for the reaction. So you will need, what we call it, pentose sugar, you need lysine, amino acid, you need high heat, you need high pH, you need low water activity to give you the perfect optimal condition to drive the Maillard reaction. So the reaction may be inhibited with sulfide. It's not really inhibited actually, it's slowed down with sulfide. How to control the Maillard reaction? So you know that the high temperature is required to give optimum rate of the Maillard reaction. So you need to keep low temperature to control. You need to regulate moisture content. You need to try to reduce the pH. For example, lemon juice, acidic environment to slow down to control the Maillard reaction. Remove the active compound. If you remove the sugar, remove the carbonyl group, you can stop the Maillard reaction, but it's really not practical to remove all the sugars from the food product, right? If it's very impractical to remove the sugar and all the amino acid from the food product. And then rapidly accelerated by temperature, significant acceleration at intermediate water activity, sugar type. I just mentioned before, same slide. The Maillard reaction products, Maillard aroma are extremely complex from the primary reactant. Primary reactant, which means that after the formation of the amino rearrangement, literally hundreds of compounds can be formed. The formation of specific targeted flavor. As I mentioned, if you have a barbecue, you can have this barbecue type of flavor, roasted, toasted, specific targeted flavor. Simultaneous generation of hundreds of individual chemical in the proper concentration and delicate balance. So it is a delicate balance during heating and storage that influences the reaction byproduct. Color also can be developed from this Maillard reaction. It is an important consequences of the reaction. Like caramel color, Maillard derived color are fully understood. What scientists still now is not much can be about the Maillard reaction in terms of reaction, but they identify all the compound that give the characteristic flavor, but the color is still poorly understood until now. So color development is in seared meat, for example, and baked bread is desirable. But if you have color development in milk, it's undesirable. You don't want your milk to turn to have browning. That is why you put your milk in your fridge in a low temperature in order to slow down or prevent the to slow down the rate of browning. So what's the beneficial uh, of the maceration? Development of crust, flavor. When you bake bread, you want that crust, you want that flavor, right? But you don't want the discolorization of milk when you're cooking. Pigment, effect of maceration in food: color, pigment produce, flavor, sweetness, effect by loss of sugar. Sometimes you can lose the sweetness of the food product because the sugar's um, been involved in the reaction. Less sugar left in the product. Reaction texture: reaction of sugar with amino acid give tough texture in dehydrated meat. Modification of protein interaction, so the the protein, the muscle protein of the meat will will become tougher, and you can have nutritional loss as well. uh, Loss of calories, loss of vitamin during the maceration. So there is a trade-off for many chemical changes that occur in food. Since reducing sugar and amino acid participate in the reaction, there will be loss of these substrates from a food system, and the reaction may impact the bioavailability of some protein. For example, if you need this protein, because of the maceration, you might not going to have this type of protein because amino acid will destroy during the maceration. Ration products may also bind to micronutrient and contribute to vitamin destruction or even inhibit digestive enzyme. So some reaction produce a product may be toxic, for example, acrylamide, some pyrazine as well. The melanidin pigment have been shown to inhibit sucrose uptake in intestine, but this statement is not well received yet because just a couple of research have been done on these things. More research needs to be carried out in order to confirm this statement here. However, some product was shown to be antioxidant. Browning reaction occurs in meat. So the browning reaction, which occurs when meat is roasted or seared, have often be referred as Maillard reaction. However, if you see your meat, you compare the lean meat between the normal meat, you know, the lean meat, for example, contain very few reducing sugar. Red meat undergoes more extensive browning than white meat because red meat contains a high amount of protein. The browning reaction in lean meat are most likely due to breakdown of the tetrapyrrole ring of the muscle protein myoglobin. Thus, the browning of the lean meat is technically cannot be said as Maillard reaction because it does not involve the reaction with the reducing sugar. Because lean meat contains very few or if any reducing sugar. So if you cook your lean meat, what happen, the reaction is technically is not Maillard reaction because the lean meat contain very few reducing sugar. If you don't have reducing sugar, it's no longer Maillard reaction. In order for you to have Maillard reaction, remember amino acids and reducing sugar. Next, caramelization. So caramelization is a browning reaction formed by heating carbohydrates. Now you have carbohydrates, sugar like sucrose or reducing sugar. Reaction can are facilitated by small quantity of acid, base, and certain salt. This caramelization reaction is entirely different process from Maillard reaction, though the result of the two processes are sometimes similar to the naked eye. If you taste, if you see the product, the food, it's kind of like very similar. You cannot differentiate between this caramelization and Maillard reaction. It's very hard with your naked eyes, with your taste bud. But the final product caramel contained a complex mixture of polymeric compound formed from unsaturated cyclic compound and the large quantities of industrial caramel color that are added to beverages such as cola drink, baked goods, confections are made by heating high conversion corn syrup in the presence of catalysts like acid and alkali. So based on this last statement here, last sentence here, you know that this is not Maillard reaction because it doesn't involve amino acid here. Only only sugar, this time in the form of corn syrup and temperature. So if you heat sugar at very high temperature, you can have caramelization going on. Okay, flavor and aroma compounds are also formed. Heating causes the dehydration of sugar molecule with introduction of double bond or formation of anhydrous rings. Intermediates such as 3-deoxyozone and furan also form. Sometimes the product can be similar, can be different because it produces lots of different products. The unsaturated ring may condense to form useful conjugated double bond containing brown colored polymer. So this is caramelization. Remember, caramelization only high temperature and sugar, okay, while Maillard reaction high temperature, sugar, amino acids. Okay, so that are the difference between these two, between the caramelization and Maillard reaction. But both are non-enzymatic browning. So we have a lots of other type of enzymatic browning, but these two are the most popular and most famous non-enzymatic browning that being used in the food production. All right. Um, so that's all for this part of lecture about the browning reaction. We have covered enzymatic browning. We have covered non-enzymatic browning, Maillard reaction, caramelization, the step in Maillard reaction, first step for formation of glycosylamine, second step amidori rearrangement, formation of ketosamine, the third step or third stage, ketosamine enolization reaction that produce sheaf-based compound or dicarbonyl compound, which then enter the Strecker degradation. Strecker degradation will produce lots of other product, but the end product is melanoidin that give you the brown colored of, that comes from the melanoidin formation. Okay, remember the enzymatic browning give you melanin, non-enzymatic browning give you melanoidin. All right, so I think that's all for today. Before we stop, you do you have any question? No? Sleeping?
No, doctor.
No.
Still here.
All right, that's good. So yeah, there's nothing more, nothing else. See you on Thursday. But I'm still thinking of what to give you for your assignment for your SCL. It's very hard. If not, I just going to ask you to present, face to face. But have you had your SCL with Dr. Swatan before?
No.
Yes.
Yes,
Yes.
It's
So
we just have to make a video and then submit.
you make a video and submit. You not present it online, right? You just submit it.
No, it's more like a video presentation.
About, may I know the topic?
Uh, um, post-harvest changes in food, vegetables, I think. Yeah.
I see. So because I think we just left with two more lectures about on microbial, on food products. Let me think of something. I will ask Dr. Swatan You already have the group, right? So
Yes.
how do you guys prepare the video? Because you're, obviously you're at your, you're at your own hometown. How do you how do you produce the video? How do you make the video with your friend? You just combine your individual videos.
Yes, we just plan out what we wanted to do, write a script, and then
So
prepare the
only
slides.
only
And
one
yeah,
only one person presents, or all of you need to present?
I'm not sure about the other groups, but for my group, we combine all of our videos.
So meaning that every single one of your group member will have to produce their own video, and then later on you combine.
Yeah, they do their own part and then combine.
Okay, maybe we can do that for the next. Anyway, I will uh, I will update later in Putra Blast. I will upload these slides. All right. If nothing else, see you on Thursday. Stay safe. I know waiting for the announcement from the PM this afternoon, whether we're going to have a more strict MCO or not. Okay.
All right.
Anyway, stay safe. Take care.
Okay,
You
thank you,
all
Doctor.
have and your family. All right.
Thank you,
All right.
thank you,
Thank you very
Doctor.
much.
Thank
Thank
you,
you. Bye.
Doctor.
Yeah, sure. Thank you. Bye.
Thank you, Doctor.